In this chapter, we will be looking at polynomial functions. In this lesson, we will be looking at the graphs of polynomial functions.
All right, now we want to talk about the graphs of the polynomial functions, and we're going to start by just kind of reflecting back on stuff that you would have seen in Math 20. So one of the things I want you to remember from that is that the x-intercepts of the graph, okay, the spots where the graph crosses the x-axis here, those are the same as the roots of the equation, or another way of describing it are the zeros of the function. I mean, we got three different ways of saying really the same thing. And it's because these ideas come from they're really distinct branches of mathematics, but they overlap at this idea. Okay, so graphically, the x-intercepts of the graph, when we're working with an equation here. Now, zeros of the function, normally what you would do here is this would be, for example, this example here would be x squared minus 6x minus 6 is equal to y. Okay, so zero of a function means we would replace the y with a 0. Now, the significance of that is that the x-intercept, okay, on a graph here are the points where the y-coordinate is 0. But that takes you, as soon as you put a 0 there, that takes you down to this thing right here, which is an equation. And when we solve an equation, we're looking for the roots. So they're all basically doing the same thing. Now, what we did in Math 20 is you would have taken your quadratic here, this x squared minus x minus 6. You would have factored that into x minus 3, x plus 2. And then, because the product is 0, then we know that either this factor was 0 or this factor was 0, in which case you bring the 3 over, in which case x is equal to negative 3, or it could be the case that x is equal to negative 2. I mean, either one of those will create a 0 in the product there. And those are going to be the x-intercepts. Okay? Now, going backwards, and this is really what how we want you to start thinking about this, that means if my graph here goes through x equals negative 2 and x equals 3 as x-intercepts, that implies that x plus 2 is a factor of the function, okay, that creates this particular graph here. Same thing, if x is equal to 3, then x minus 3 is a factor of that function. Now, let's take a quick look at this next one here. What about a cubic? Okay, here's our cubic. Now, in this case here, we're not going to go from the equation to this thing. We're going to kind of hint at what the equation would be. This is going through negative 1. So x equals negative 1. That implies x plus 1 is a factor. X equals 2, okay, where I cross x equals 2 right there, that implies x minus 2 is a factor. And then over here, when x equals 4 along the x-axis, that implies x minus 4 is a factor. And so we might write this out right now. We might say that the equation is y equals, okay, x plus 1, x minus 2, x minus 4. They're all factors multiplied together. Now, that's not 100% true. And the reason for that is I could very easily draw a graph that's a little different that does the same thing though. Hits there, goes up, hits there, comes back down, hits there. Okay, still hitting the exact same x-intercepts, but it is a different function. But what differs about it is what we call the vertical stretch. And that's caused by having a coefficient up front. But that right there is the general form really of that expression there, okay? It's kind of hits all of the different functions that hit those x-intercepts. So again, notice that we've got two turning points, okay? Has two turning, sorry, that should say two changes in direction, but that gives us a degree of 3. It has 3 x-intercepts, which is a good indication that that's a cubic. It's not doesn't guarantee it, but it's a pretty good indication. And in this particular case here, notice that it starts in quadrant 1 and drops down to quadrant 4, okay? That indicates to me that this is a negative leading coefficient. So I don't know what the value of a is, but I do know that it's going to be negative. Okay, now, just before we get into some specific examples here, let's take a look here. So from the last lesson, we had the following connections here. So remember that the degree is the highest exponent or number of times it changes directions. Degree is the maximum number of x-intercepts a graph can have, so you want to keep those both in your head as you're looking through this. Degree in the leading coefficient tells the end behavior, in other words, quadrant to quadrant, when you go from the left side of the graph to the right side of the graph, which quadrant? Are you starting in 2 or 3? Are you ending in 1 or 4? And then when it's in expanded form, okay, and that's that has to be like that, then the constant is always going to be the y-intercept. All right, let's take a look at some questions here.
Sketch the following polynomial functions with the given characteristics.
Okay, so now we're going to put this stuff all together and see what we can come up with. Actually, we'll zoom in a little bit here, so it's, whoops, wrong way. So it's a little bit easier to see. So extending from quadrant 2 to quadrant 4, having two x-intercepts. Okay, so now if it's going from 2 to 4, that has to be an odd negative degree. Okay, odd degree negative function here. Now to have two x-intercepts, now the smallest odd that I can think of, okay, would be a cubic. But a cubic is naturally going to want to have 3. But I don't want that. I only want 2, which means one of them has to be going straight through, and it doesn't matter, and the other one really has to come up and just touch it. Now, I can come down, touch it, and then go through, or come through, come up and touch it. It doesn't really specify here, so let's just do it like this. It's going to come down, up, touch it, then come back down. Okay, and there's our first one. Now, let's take a quick look at this next one here. Now, this one says that the range of the function we're looking for is less than or equal to 4 and has one turning point. Okay, well, as soon as you say one turning point, you can pretty much rest assured that it's going to be like a parabola. Okay, and it comes up to 4. So here's this line right here at 4. It's going to come up to that. So basically, we're going to come up, we're going to hit 4, and then drop back down. And that's what that's going to look like. Actually, that's a pretty good parabola, if I do say so myself. Okay, let's look at the next one. What does it say? It says decreasing, one x-intercept, and no turning points. Okay, no turning points here suggests a linear function. Okay, so, and one x-intercept decreasing, so basically just something going down. Now I can draw that kind of wherever, but that's basically the gist of what we're being described here, okay? Decreasing, one x-intercept, no turning points. Okay. Positive leading coefficient. Okay, now if it's odd, that means it's going up. If it's even, it's opening up. Constant of -3. Okay, so that means it's going to have a y-intercept of -3. We know that. There's -3. And 2 turning points. Okay, positive leading coefficient, 2 turning points, suggests a cubic. Okay, suggests a cubic. Now, it doesn't have to be a cubic. Probably could draw this as something else here, but okay, at least a cubic. So let's do that here. So let's come up, comes around. Let's say it drops back. We're going to drop down through that x-intercept, change directions again, and go back up. So there we go. Positive leading coefficient because I'm moving up. Goes through a y. It has the constant of -3, which is the y-intercept, and 2 turning points. That's what they're describing. This next one here, degree of 2. Okay, so it's going to be quadratic. Negative leading coefficient opens down and extends from quadrant 3 to 4. Now, they almost didn't need to say that last little bit there, because if it's degree 2, so even degree, and a negative leading coefficient, it has to open down. So this thing really, you can maneuver this around wherever you want. You can place it wherever, but it's going to go from 3 to 4, okay, and open down there. This last one here, 2 turning points. Okay, that implies that it's probably going to be cubic, extending from quadrant 2 to 4, so from here to here. Okay, and the constant term of 7. Okay, well again, the constant term we link with the y-intercept. Okay, just going to get a little bit more lead there. So 2 turning points extending from quadrant 2 to 4, so it's going to come down, curve up, come down, and there we go. Ends in 4, started in 2. So something like that. It doesn't have to be. You can kind of slide this thing along. As long as it goes through 7 on the y-axis, that's what we're looking for.
Complete the following table.
Right, now for this question, let's kind of take everything in stride here. We're going to go down the columns here. So type of function, and we've got the graphs here, okay? So first of all, the degree. So when I look at this right here, I see 2 turning points. Best guess is that's a cubic. Okay, Could be something else there, but that's really forcing the discussion, and it's implying that there's something else going on here that I'm not seeing. 3 is easy. Here's another one with 2 turning points. Degree is 3. This one here has a single turning point, so I'm assuming this is a degree 2, a quadratic. Okay, good. The next column says the sign of the leading coefficient. Okay, well, this extends from quadrant 2 to quadrant 4, so it's dropping, so negative. This one extends from quadrant 3 to quadrant 1. It's rising, positive. This one goes from quadrant 3 up and back down to quadrant 4. It's a parabola that opens down. Leading coefficient's got to be negative. Okay. This one here, number of turning points. Well, it's cubic, and I see that the number of turning points here is 2. I can see them. They're there and there. For this one, same thing. There are 2 turning points. I can see them there and there. Now, this one here has a single turning point. It has a maximum value at x equals, what have we got here? At x equals -1. And the maximum value here is going to be 9. The thing goes up to 9 and then drops back down again. That's the kind of behavior you'd expect from an even degree, whether it's quadratic or quartic or 6th degree or so on. Okay, x-intercepts. Well, looking at the graph here, looks like we're hitting it between at -3. This looks like 1 here, so -3 and 1. And this is just reading it right off the graph here. Now, sometimes that's not always easy to do, but that's all we're doing. So here, this is -4, looks like -3, and then +2. So -4, -3, +2. This one down here looks like -4 and +2. Okay, what else? Factors. Oh, okay, factors. Okay, so here we go. That I don't even need to slide this thing over for. If my x-intercepts are -3 and 1, my factors will necessarily be x plus 3 and x minus 1. Okay, so x equals -3, bring the 3 over. X equals 1, bring the 1 over. There we go. Here, oops, sorry. If it's -4, then one of my factors is x plus 4. It's -3, then one of my factors is x plus 3. And if it's +2, then the other factor here would be x minus 2. And then down here, if my factors are -4 and 2, then one of my factors is going to be x plus 4, and the other factor here would be x minus 2. Okay? Now, y-intercept or constant? Okay, y-intercept. Well, I gotta look here. I'm just going to read that off. Ooh, that's... Okay, let's take a quick look here. But look at the scale. Okay, this goes a tick and then to -4. Well, that tick's got to be 2. This is going to be down here at -2, which means that looks like my y-intercept or the constant term would be -3. I mean, that's just best guess there, but -3 looks pretty good. This one right here, oh, this one's not terribly clean here. This has got to be -5, -10, -15, -20. This has got to be -25, so maybe -24, maybe? Hard to say when I'm reading off like that. This one right here, okay, well this one is convenient. This one's nice. It goes through 8, nice and cleanly, so it's going to be 8 there. Okay, finally, domain and range. Well, this one starts high, ends low, and goes forever left and right. Well, that means my domain will be all reals. Oops, sorry, I wanted to write R there for range. My range will also be all reals. Now, you expect that kind of behavior from an odd degree. This one here, the second one, is also a cubic, and so I expect the same behavior. My domain will be all reals. My range will be all reals. But I don't expect that kind of behavior for an even degree. This is an even degree. It's a quadratic, opens down. Now, my domain is still going to be all reals. Now, and that's because all polynomials will have a degree that's, a domain that's all reals. There will be no limitations to it. The range, on the other hand, will be a little different here. In this case right here, this thing hits a maximum value of 9. Okay, if you follow the point here, just slide along this curve here, the largest y coordinate that we're going to get to is 9, and then it drops back down again. So the range is, I can state this by simply saying that all of the y coordinates are going to be less than or equal to, because it does get up to 9, but less than or equal to 9. Okay, and there we go.
Complete the following table.
Now for this question, we're essentially going to do something very similar to what we did in the previous question. Just this time we're going to be working with the equations here. Okay, so let's run through this really quickly. And actually, this is nice because we can kind of see everything all at once here. So type of function. Notice that I've got 3 linear factors. This is a degree 1 factor, degree 1, degree 1. 3 of them means this is going to be a degree 3, and that's what we call a cubic. Okay? In fact, it's a positive cubic because the leading coefficient here, I can see that there's no negatives in front. It's going to look like this. This one over here, I've got 2 linear factors, but this one shows up twice. This is like having x plus 1, x minus 2, x minus 2. So it's still cubic. There's still a degree 3 here. But in this case, there is a negative in front, meaning this one's going to drop down. So it's going to look something like that. This one here has got a degree of 1. Okay? And that makes this a linear function. And here, this one's all nicely expanded out for us. The degree is 2, so this is quadratic. That's nice. Now, leading coefficient. Oh, that's a diabolical little one here, because in order to do that one, you got to expand this stuff out here. So now, but when I do that, the highest degree term here is going to be from multiplying this x by this x by this x. Now let's just do that real quick. That's going to be 4x by x is 4x squared, times this x is going to give us 4x cubed. That will be the highest degree term in that expansion. And I get it from just multiplying the x's together, not multiplying it against any other numbers, just the x's. Now that means that my leading coefficient is going to be 4, and I'm going to end up with a cubic, so degree 3. Here, same thing, but I might want to start with this term because it's being squared. So it's x, it's going to end up being x times x, or x squared, multiplied by that x is an x cubed, and then there's a negative 1 in front. So by just multiplying those x terms together, because that would give me the highest degree term, as soon as you start multiplying the x's by the negative 2's and stuff, you're going to get smaller degree terms because you're going to introduce the numbers in place of the x. But x's all together is going to get you x cubed, and that negative in front, negative x cubed. So the leading coefficient is going to be negative 1, and again, degree 3. These two at the bottom here, much more straightforward. There is only the one x here. It's linear. Its leading coefficient is negative 1/2, and its degree is 1. Here, the highest degree term is this x squared, so it's degree 2. And the leading coefficient is just 1. You're not seeing anything in front, so it's got to be 1. So now, end behavior. Well, all I need are these 2 bits of information here to know what the end behavior is. This is a cubic with a positive leading coefficient, means it's going up. So it's going to go from quadrant 3 to quadrant 1. Okay? And actually, you can put those arrows both ways, but because depending on which direction you're going to move here. This one is a negative cubic, so it's going to start in quadrant 2 and it will end in quadrant 4. This is a negative linear, so it's going to drop down. So actually it's going to be identical to the one above it. It'll start in quadrant 2, end in quadrant 4. This is a positive quadratic, and a positive quadratic opens up, so it's going to go from quadrant 2 over to quadrant 1. Okay, that's all I needed, just those 2 bits of information here. X-intercepts. Okie dokie. Now, when it's in factored form, that's actually pretty easy for me to deal with here. All I have to do is unravel these factors. Okay? Now, in this particular expression here, these 2 will be quite easy. Okay? Because if x minus 3 is going to give me a 0, going to create a 0 for to make this an x-intercept, just bring the 3 over. So it's basically like this. What we're going to do is we're going to take each one of those factors here. So for example, I'll start with 4x plus 2. I might as well. When this equals 0, the result is going to be an x-intercept for that graph. So bring over the 2, divide by 4, one of the x-intercepts is negative 1/2. So here we go. Negative 1/2. Then I had x minus 3. That equals 0 when x is equal to 3. So another one of my x-intercepts here is going to be 3. And then we had x plus 10 equal to 0, and that's going to go to 0 when x is equal to, whoops, sorry, almost couldn't see it, negative 10. For this one right here, I've really only got the two terms here, so that's going to go to 0 when x plus 1 is equal to 0, and that's going to be negative 1. That other factor here was x minus 2, and this will go to 0 when that'll become an x-intercept when x minus 2 is 0, or where x is equal to 2. Down here for this one, I just got to set this one equal to 0, so that's going to be 0 is equal to negative 1/2 x plus 5. A little bit more work involved here. Bring the 5 over. Negative 5 is equal to negative 1/2 x. Well, the negatives will cancel, and I can simplify this by multiplying both sides by 2, and I get x is equal to 10. So that's the x-intercept. For this last one, before I can come up with the x-intercepts here, I actually have to put this in factored form. So I'm going to spend a couple minutes here and just factor this. That first term is just x squared, with the coefficient is just 1. So that really, the easiest way to interpret that is just x and x. And then I'm looking for two numbers whose product is negative 2, and then where the sum is negative 3. Okay, well, that does not appear to want to happen. In which case, if I can't factor that, what do I do? Okay, now bear in mind this is negative, so when I put those in here, one of them's got to be negative, one's got to be positive. So like if you put negative 2, positive 1, well, that's not going to do it, because negative 2 and positive 1 is going to get you negative 1. If you make this positive 2 and negative 1, it's still not going to give you that middle term here. So that isn't going to work. So what do I do when factoring doesn't work? Well, what I do is I use the quadratic formula. So x is going to equal the negative of the b value, so that's going to be positive 3, plus or minus the square root of b squared, so negative 3 squared, there's your 9, minus 4 times a, which was 1, times c, which is negative 2, so it's going to be, well, it's going to be minus 4 times negative 2, and this will all be over 2 times 1. So 3 plus or minus, well, okay, what's that? That's going to be negative 4 times 2 is going to be positive 8 plus 9 is 17. So that's going to be 3 plus or minus root 17 over 2. Well, I can't simplify that. That's as good as I'm going to get here. 3 plus or minus root 17 over 2. Well, that's okay. Finally, we're going to fill in the constant. Now, the constant for these top two here is going to be found when just the numbers in each one of those factors gets multiplied together. Because remember, when you expand this out, everything kind of gets distributed to everything else here. But the first term is going to be when you multiply the first terms in every case together. The constant will be when I multiply all of those numbers together. So 2 times negative 3 is negative 6, times 10 is negative 60. So that would be my y-intercept. Here, I just got to pay attention to the fact that there's a square here. So when I multiply the constants together, first of all, notice there's a negative 1 out front. So negative 1 multiplied by 1 multiplied by negative 2 squared. Well, negative 2 squared is 4. Times 1 is 4. Times negative 1 is negative 4. For the last two, it's actually a heck of a lot easier because it's just going to be the constant term. It'll be 5 here, negative 2 here. 5 and negative 2. And that is how we find all of that information from those equations.